So up to this point, we gave a formula for the derivative of a power function, and then we discussed numerous rules that would give us derivatives of functions that were obtained by combining various power functions in various ways. But so far, we're still not able to calculate the derivative of things like the trig functions, of things like the exponential and logarithmic functions, and that's what we're going to do today. We're going to give the derivatives of sine of x and cosine of x, and we're going to use those formulas to find the derivatives of tan, cotangent, cosecant, and secant. Then we're going to give the derivatives of the natural exponential function e to the x and the natural log function natural log of x. And we're going to briefly look at the derivatives of exponential functions and logarithmic functions with non-natural bases, b to the x and log base b of x. Now, several videos ago, I think it was back, maybe video 9, we argued graphically that the derivative of sine x looked an awful lot like cosine x. And that turns out to be absolutely true. The derivative of sine is equal to cosine. Meanwhile, if you take the derivative of cosine, you get, and here be careful, the derivative of cosine is equal to negative sine x. So, having these formulas, let's try and answer a conceptual question. Let's try and describe all the points at which the tangent line to sine of x has a slope of 1. In order to answer this question, we need to remember the fact that the slope of the tangent line is equal to the derivative. So what we're looking for are locations where the derivative of the function f of x, the slope of that tangent line, is equal to 1. Now the function in our problem is sine of x, and we were just told that the derivative of sine of x is cosine. So as a result, what are we trying to solve? We're trying to solve the equation cosine of x equals 0. The solutions to this equation are all the locations where the tangent line to sine has a slope of 1. Now, in order to answer this question, you are going to have to go back in time to when you took trigonometry. There are a couple of different ways to think about how to answer this question. I think one of the more accessible ways to think about it is to think about the unit circle. Remember that cosine on the unit circle, cosine was what gave you the horizontal position. So our goal is to make the horizontal position on the unit circle equal to exactly 1 unit, positive. And since the circle is of radius 1, the only way to get the horizontal coordinate to equal positive 1 is to be all the way on the far right side of that unit circle. So at which angles is that achieved? That's achieved when x is equal to the 0 angle. The 0 angle is pointing to the positive horizontal direction, so it will point straight to the right, and it will point to a location where we have a horizontal coordinate of 1. But that's not all. If I decided to do a full 360 and wrap all the way around, I would still be pointing to the far right side of the unit circle. So x could be equal to 2 pi. But there's nothing stopping me from doing another 360 and another and another. Nor is there anything stopping me from doing a full 360 in the opposite direction. So there are infinitely many solutions to this equation. In general, the format of these solutions is 2 pi times some multiple, 2 pi times some number called k, where k is an integer. You may see this written, k is an element of z for short. So let's confirm this graphically. Here I have the function sine of x, and at the angle where x is equal to 0, our tangent line does indeed have a slope of 1 unit, because if I go over by 1, I have to go up by 1 to get back onto the line. The same thing is true with the tangent line over here at x equals 2 pi. At x equals 2 pi, our tangent line still has a slope of 1, and likewise at x equals negative 2 pi, sine still has a tangent line with a slope of positive 1. Once we know the derivatives of sine and cosine, we can find the derivatives of all the other trigonometric functions. Because, for example, tangent of x was just equal to sine divided by cosine. So I could find the derivative of tangent using the quotient rule. The same thing is true for cotangent, which is just opposite cos divided by sine. The same thing is true for cosecant, which is just 1 divided by sine. And the same thing is true for secant, which is just 1 divided by cos. So what I'm going to do is I'm going to find the derivative of tangent, and I'm going to leave the remaining 3 functions to you as part of the exercises for today, because the calculations for the others are going to be extremely similar. I can use the quotient rule, which says low d high minus high d low all over low squared. So the low function is cosine. Multiply that by the derivative of the high function, sine, minus the high function, sine, times the derivative of the low function, cosine, all over the low function squared. Now, the derivative of sine, that was just cosine. So we have cosine times cosine. The derivative of cosine, remember that the derivative of cosine was negative sine. So we have minus sine times minus sine. Now this is one of the rare situations that you will actually see me simplify this. Cos times cos is just cos squared. Minus sine times minus sine is positive sine squared. Now I hope that you recognize this quantity in the numerator, because this quantity appears in the most important equation in trigonometry, which is the Pythagorean identity. The Pythagorean identity says that if you take cosine squared plus sine squared, the result of that will always be equal to 1. So what's the derivative of tangent? The derivative of tangent is equal to 1 divided by the square of cosine, which is the same thing as secant squared. Now, as you're in the exercises and you're working on the derivative of cotangent, cosecant, and secant, the question is, of all these derivatives, of all these different trig functions, which ones might be worth your time to actually memorize? based on my personal experience, the only ones that really should be memorized of the derivatives of the trig functions are the derivatives of sine and cosine for sure, and to a slightly lesser extent the derivative of tangent. And I also find that it can be useful sometimes to remember the derivative of secant. But the most important ones to memorize, to actually know by heart, are sine and cosine. Now let's use some of these formulas in combination with some of the rules that we've studied up to this point. Someone gives us the function which is the product of x and tangent of x. And what they want us to do is find the derivative of this product. So for that, I can just use product rule, which says that f prime of x is equal to the first function times the derivative of the second function plus the second function times the derivative of the first. The sum of the two products, where in the first term one function has a derivative, in the second term the other function has the derivative. Now in the previous exercise we saw that the derivative of tangent was simply secant squared. And the derivative of x, we know, is 1. So the term in the back is 1 times tangent. The term in the back is just tangent. And this would be the derivative of this function, x times tangent of x. Now trigonometry has a way of popping out of the bushes when you least expect it. You'll be going along, you'll survive for years, and then all of a sudden someone says, you remember law of sines, which you haven't used in 3 years? All of a sudden you're going to need to know it. And that can arise in this class as well. For example, here. In this situation, we're given the function sine of 2x, and we're asked to find its derivative. But we have a problem because we don't have a formula for sine of something other than x. We only have a formula for sine of x period. So what I'm going to do is I'm going to use a trig identity to try and rewrite f of x slightly. I'm going to say, back 500 years ago, I remember learning about something called the double angle identity, which says if you take sine of 2 times an angle, then that's the same thing as 2 times sine times cos. So what I'm really trying to find the derivative of is 2 times sine of x times cosine of x. And this is wonderful because this is now expressed as a product of sine of x and cosine of x, and we have formulas for the derivatives of those factors. So using the constant multiple rule, I'm going to set the constant multiple of 2 aside for a moment. And I'm going to find the derivative of the product sine times cosine. So I have the first function times the derivative of the second function, cos, plus the second function times the derivative of the first, the derivative of cos is what? Sine or negative sine? the derivative of cos is negative sine. And the derivative of sine is positive cos. So what is f prime in this situation? F prime is equal to 2 times negative sine squared x plus cosine squared x. Now some of you may see this and think that this might be another opportunity to use the Pythagorean identity. But we won't be able to use it in this case because of the minus sign on the sine squared. Notice that when we used Pythagorean identity before, both cosine squared and sine squared were positive and they were being added together. Contrast that with what we have here. Yes, cosine squared has a plus, but sine squared has a minus. So this time these quantities are being subtracted. And as a result of that, we cannot use Pythagorean identity to simplify this function dramatically. There is a way to simplify this, but it relies upon a slightly more obscure trig identity that I wouldn't actually expect you to remember or to know at this point. The final really important class of functions are the exponential and logarithmic functions. And of these, the most important are the natural exponential function and the natural log function, whose basis is this really important number e. If you take the derivative of e to the x, a quite remarkable thing occurs. If you take the derivative of e to the x, literally nothing happens. The derivative of e to the x is e to the x. So put another way, the rate of change of e to the x is the same as the y value of e to the x. Put another way, the slope of the tangent line to e to the x is always exactly the same as the y value of e to the x. What a remarkable property. The next derivative worth knowing is the derivative of the natural log function. Now when I write natural log, I have a habit of writing it with a capital L, just because lowercase l's tend to look like ones. So I'm going to write natural log with a capital L of x. The derivative of this function is 1 divided by x. So the question is, what is the derivative of b to the power x? What is the derivative of log base b of x? The truth is that generally speaking, it's not worth actually learning or memorizing the derivatives of logarithmic or exponential functions whose base is not e. These guys are, relatively speaking, unimportant compared to the natural exponential and the natural logarithm, which, as the name suggests, have a lot of natural real-world applications, whereas these other two are not quite as broadly applicable. For these two, I find that I encounter them so infrequently that I usually just look them up. I'll splash the formulas on the screen real quick, but the truth is usually I just look up these formulas on the rare occasion that they are necessary. Which of these is worth memorizing? You will certainly be expected to know the derivative of e to the x, and you will certainly be expected to know the derivative of the natural log, but these other two, as I've said, you really don't need to memorize them. They're pretty rarely used. Let's calculate the derivative of this slightly monstrous function. In the numerator, we have e to the x times cosine of x, and in the denominator, we have natural log of x. So let's see if we can figure out what is the derivative of this monster. Now f of x is composed of one function divided by another. The low function is given by the natural log of x. And we were just given a formula for the derivative of natural log. The derivative of natural log is just 1 over x. The high function, however, is equal to e to the x times cosine of x. Which means if we wanted to find the derivative of the high function, we would have to use product rule just to find the derivative of the upper function. So first times the derivative of the second plus second times the derivative of the first. The derivative of cosine is negative sine. So I have negative e to the x times sine. And the derivative of e to the x is just itself. So I have e to the x times cosine. Finally, we have all the ingredients that we need to assemble the quotient rule formula. Take the low function, which is natural log of x, and multiply it by the derivative of the high function, which means I'm going to multiply it by this entire expression, derivative of the high function. Then take the high function, which is e to the x cosine x, and multiply it by the derivative of the low function. So e to the x cosine x times 1 over x. And then all of that all over natural log of x quantity squared. Beautiful. Thank goodness we don't have to simplify this, right? What a pain. At this point, we can calculate the derivative of almost anything, given enough time and patience. However, there is still one rule that we need to cover, which is what do you do if you have a composition of two functions? What do you do if, for example, if you were taking the derivative of something like cosine, where the exponential function is inside? I don't know about you, but I'm not aware of any trig identities that I could use to rewrite this function so that it would be vulnerable to product rule, quotient rule, or one of the other rules that we have already studied. So we need one more rule, the final rule, which is chain rule. Which handles compositions of functions. Situations like this, where we have one function, e to the x, which has been placed inside of another function, cosine of x. And that will be coming in a couple of days. That concludes today's material. We talked about the derivatives of the sine and cosine functions. Then we introduced the derivatives of the exponential and the logarithmic functions. Once we had the derivative of those basic functions, the basic functions sine, cosine, e to the x, and natural log of x, we practiced using those formulas in combination with the product rule and the quotient rule.